There is a silence in the wind that only the experienced recognize. To most, a gentle breeze shifting directions or slowing down feels like a gift, a break from relentless summer heat, or a moment of calm before sleep. But to those who understand storms, it can signal the first atmospheric anomaly, subtle, quiet, but deeply important. Before hurricanes form, wind speaks in small ways. On a normal day, wind follows predictable paths shaped by global pressure systems and surface temperature gradients. Over the ocean, trade winds flow steadily, pushing air masses westward. But as ocean water heats and begins to feed the sky with moisture, something changes. That once steady wind begins to hesitate. It may slow just a little, it may start to curve or become inconsistent. Sometimes, the direction changes entirely. Not by much, just a few degrees. But it's enough. This change isn't random, it's a signal. What's forming beneath this subtle shift is vertical wind shear, a crucial element in storm development. Wind shear refers to the difference in wind speed or direction at different altitudes. Under normal circumstances, wind shear can disrupt storm formation by blowing the tops off clouds and scattering heat. But when wind shear weakens, it creates a more stable vertical structure. Moist air from the sea rises, and with no resistance, clouds stack higher and higher. It is the beginning of vertical organization, a necessary step for any powerful storm. Scientists at NOAA have studied these moments for decades. Data from weather balloons, satellites, and Doppler radar paint a consistent picture. Small wind shifts often precede major cyclonic development. In the hours or days before a named storm is declared, surface winds may slow to 10 to 15 miles per hour below their seasonal norm, particularly over warm ocean patches. At the same time, upper-level winds, usually racing far above at 30,000 feet, calm down as well. The atmosphere becomes unusually quiet, like it's holding its breath. That quietness isn't just in the wind, it's in the data. Meteorologists often describe it as a void or stillness zone. Satellite imagery shows minimal cloud movement. Buoys record drops in surface turbulence. Aircraft that fly hurricane missions frequently report unexpected stability before the chaos. This behavior isn't an absence of weather, it's the orchestration of it. The stage is being set. One of the most fascinating aspects of this phase is its invisibility. The human eye can't detect it from the shore. You could be standing on a beach as the wind softly shifts westward, unaware that thousands of feet above, air currents are lining up like gears in a machine. There are no thunderheads yet, no rain, no spiraling clouds on satellite images, just a small but critical deviation in flow. It's also during this time that temperature changes within the wind become noticeable to instruments, and sometimes to the skin. The wind, though gentle, carries heat. If you're near the coast or aboard a vessel, you may feel it, a warm edge that wasn't there before, almost like the breeze is coming from the wrong place. This warmth is a physical manifestation of oceanic energy being transferred into the atmosphere. Heat is the currency of storms, and it begins its work quietly. Research from Junion et al. 2014 highlights another important player during this phase, the Saharan air layer, SAL. This dry, dusty air mass originating from North Africa travels westward across the Atlantic. It can suppress or delay storm formation, but it also affects wind patterns. When the SAL retreats or becomes less dominant, winds near the equator regain moisture and stability. This transition often triggers the initial drop in wind shear, setting the stage for pre-storm development. In essence, the exit of dry air is the green light for the atmosphere to begin spinning. But not all spin is dramatic. Early-stage cyclonic motion is so broad and weak that it often goes unnoticed by traditional observation. It may show up in satellite infrared bands or in the sudden alignment of cumulus clouds across hundreds of miles. Scientists call this incipient vorticity, the barely there rotation that signals nature's intent. At this point, the wind is no longer just a carrier of air. It becomes a conveyor of structure. What follows is a slow tightening. As warm, moist air continues to rise, Coriolis force, a result of Earth's rotation, nudges it into a curve. The once straight wind begins to loop, still wide, still slow, but it's closing in. This is where surface observations become vital. Meteorological stations along coastal zones, particularly in the Gulf of Mexico and Western Atlantic, are equipped with high-sensitivity anemometers. These instruments can detect minute changes in direction and speed over time. A consistent reading of veering wind, from northeast to southeast over a 6 to 12-hour period, is often an early indicator that a cyclonic circulation is developing offshore. Add in slight temperature increases and dropping surface pressure, and forecasters begin to watch closely. These conditions may not look like much to the public, but in a hurricane center, they light up screens with caution. One critical moment in this phase is the convergence of surface winds. Normally, air near the surface flows outward from high-pressure areas, but when pressures drop over a patch of warm sea, nearby winds begin to move inward. This convergence lifts moist air upward, forming larger and more organized cloud clusters. If this process sustains, it becomes self-reinforcing. The more wind converges, the more air rises. The more air rises, the more pressure drops. And the more pressure drops, the more wind is pulled inward. A feedback loop begins, and with it, the architecture of a storm. This feedback loop doesn't need a name to start. It can begin hours or even a full day before the National Hurricane Center declares a tropical depression. It may not appear dramatic on satellite images, it may be missed by local news, but within the atmosphere, it's already real, already working, already alive. And yet, to the untrained eye, the wind still feels calm. That's the danger. Storms don't always announce themselves with thunder or lightning. Sometimes they begin in whispers, a breeze that suddenly feels warmer, a gust that arrives from an unusual angle, a pause in what was once a steady flow. This early phase, the silent choreography of wind, is where preparation meets awareness. By the time the clouds spin fast enough to see, it's already well underway. As the low-level winds begin their slow inward spiral, a vertical alignment emerges, an essential structural shift in the atmosphere. What was once scattered movement across various layers begins to unify, with winds at the surface, mid-level, and upper troposphere cooperating instead of competing. This coordination is one of the clearest signs that a tropical cyclone may soon form. Yet even here, the signs remain subtle. Wind speed might not yet be extreme, perhaps only 15 to 25 miles per hour at the surface, but the precision of its direction is what matters most. Instead of flowing westward with the trades or drifting randomly, the wind begins to circle. In maritime reports and coastal observations, you might see the term cyclonic curvature, a gentle bending of airflow that suggests the embryo of a storm. These directional signatures are often confirmed using scatterometer satellites, which measure surface wind vectors across vast ocean regions. A loose but organized counterclockwise pattern in the northern hemisphere is a red flag for tropical meteorologists. The pressure gradient also begins to tighten. That is, the difference in atmospheric pressure between the center of the developing system and its surroundings becomes more pronounced. As pressure drops in the center, surrounding air accelerates toward it. The wind responds, it speeds up, not suddenly, but steadily. And as it accelerates, the system begins to rotate more clearly. At this stage, mid-level convergence increases. That means not only is surface air spiraling inward and rising, it's now pulling surrounding air from thousands of feet up toward the center. The storm begins to stand upright, like a spinning column of moisture and motion. This is a tipping point. The system now has enough symmetry and self-reinforcement to maintain its energy, even if environmental conditions fluctuate. It's also when wind no longer feels off, it begins to feel intentional. Local weather stations, especially those on small islands or ocean platforms, might report an unusual sequence. Wind from the east in the morning, shifting southeast by afternoon, and due south by evening. When logged hourly, this shift looks like a smooth arc. Paired with falling pressure and rising dew points, this sequence tells meteorologists that the circulation is not only forming, it's strengthening. The atmosphere is beginning to funnel energy into rotation. But perhaps the most defining atmospheric cue of this stage is the onset of banding. Banding is when clouds, and the winds that shape them, begin to organize into long, curved arcs, spiraling around a central point. These rain bands are not yet ferocious, but they are directional fingerprints. Their curvature matches wind motion, and in satellite imagery, they appear like early sketches of a hurricane's arms. The existence of these bands confirms that wind is no longer just moving, it's organizing. Wind shear, which once could tear such systems apart, is now either absent or offset by strong lower-level convergence. The Saharan air layer, if present at all, has likely retreated to the north, allowing moist tropical air to dominate the lower and middle levels of the atmosphere. This creates vertical consistency, where winds from the surface to 30,000 feet align in both speed and direction. When this happens, a storm doesn't just survive, it intensifies. And within this organized wind field, a core begins to form. Initially, it's not a clear eye. There may be no break in the clouds, no visible hole. But data from aircraft reconnaissance missions, particularly those flying through the potential center, often record rapid drops in pressure, followed by strong wind bursts and then relative calm. These changes happen over distances of just 10 to 30 miles. It's the rough draft of an eye, what meteorologists call a developing core. And it only becomes visible because the wind around it has tightened and accelerated enough to build a wall of rising air and outward spinning clouds. This tightening process is deeply tied to the heat and moisture provided by the ocean, but it's orchestrated by wind behavior. The speed, direction, and curvature of that wind shape the entire system's future. Strong inflow at low levels feeds the central updraft. Weak upper-level wind shear allows the storm to grow vertically, and mid-level rotation begins to wrap drier outer air away from the center, insulating the developing core like a lid on a pressure cooker. But not every system follows the same wind choreography. In the presence of upper-level troughs, elongated low-pressure zones in the upper atmosphere, wind direction at high altitudes may briefly diverge. Instead of perfectly aligned columns, developing storms may be tilted. When this happens, the storm struggles to stack vertically, and winds may begin to shear the top off. These systems often fail to intensify or lose organization quickly. But if that trough exits or weakens, the storm can rapidly realign. Within hours, wind fields can lock back into place and intensification resumes. It's this sensitivity to wind structure that makes forecasting so difficult. Small changes in upper-level jet streams, mid-level steering currents, or surface convergence can completely alter a storm's path or power. That's why hurricane models ingest millions of data points about wind every hour. Some from satellites, others from weather balloons, and the most critical from Hurricane Hunter, aircraft flying directly through the storm. These missions measure wind speed and direction at multiple altitudes, helping to confirm whether a system is organizing or unraveling. But even without aircraft or radar, the human body can sometimes feel a change. Fishermen in the Caribbean, coastal residents in the Gulf, and islanders across the Pacific often speak of storm wind as distinct from everyday breeze. It smells heavy, it feels warmer, it behaves differently. It doesn't gust as much, but it flows more steadily. It may sound subtle, even superstitious, but often these instincts match what instruments confirm, a shift in the wind's intention. By the time these wind shifts manifest clearly at the surface, the clock is ticking. Tropical depression, tropical storm, hurricane. The titles change, but the wind builds the story. This is the point where preparedness becomes urgent. Authorities begin issuing watches and warnings. Emergency response teams activate. Residents board windows, fill gas tanks, and review evacuation plans. And behind all of it, underneath the alerts and announcements, is wind. Wind carrying messages from the ocean to the sky. Wind reshaping clouds into spirals. Wind wrapping heat into motion. Wind reminding us, with every quiet shift, that nature doesn't need thunder to speak loudly. It just needs patience and direction. And when both align, the storm is no longer coming. It has already begun. The architecture of a hurricane is sculpted by wind, layer by layer, mile by mile. As the circulation strengthens, wind behavior begins to reveal the storm's inner structure. The outer bands stretch across hundreds of miles, but the core tightens. Like the gears of a machine clicking into place, every layer of wind must align for the cyclone to evolve into something more organized, more powerful, more dangerous. This phase is marked by a phenomenon known as vortex alignment. At its core, this refers to how the storm's rotating column of air becomes vertical. Without this alignment, a storm may look impressive on satellite images, but remain disorganized internally. The wind, in such cases, works against itself. Upper-level outflow shears away the heat and moisture rising from the surface, essentially decapitating the storm before it can fully form. But when vortex alignment occurs, everything changes. The winds at all levels begin to work together. At the surface, inflow continues to drag warm, moist air toward the center. In the mid-levels, that air spirals upward, pulled by pressure drops and the buoyant force of rising heat. And at the top, the storm vents. Air flows outward in symmetrical channels, creating space for more surface air to rush in. This is when storms become self-sustaining. A balanced wind profile, from sea level to the upper troposphere, means that the storm is no longer fighting the environment. It is the environment. The entire atmosphere in its vicinity bends to accommodate the cyclone's energy cycle. It breathes in moisture through low-level winds, converts that moisture into latent heat, and expels spent air at the top, all through wind vectors now locked into near-perfect choreography. As this happens, surface wind speeds rise sharply, from 30 miles per hour to 50, from 60 to 74 miles per hour, the threshold for hurricane status. But it's not just about speed, it's about symmetry. Doppler radar and satellite data often reveal that at this stage, wind fields become circular, not elliptical. This shift is crucial. A storm with uneven wind fields will wobble, lurch, and weaken over time. But a storm with symmetrical wind distribution can sustain itself, sometimes for days. That symmetry is why hurricane-force winds aren't just dangerous, they're diagnostic. They tell scientists that a storm has achieved equilibrium. And they often signal the formation of an eye. The eye of the storm is a direct consequence of extreme wind alignment. As surface air spirals inward, it reaches a point near the center where it can no longer go down because the pressure is already too low. Instead, it shoots upward, forming the towering eye wall. That eye wall becomes the storm's engine, and the eye is its exhaust chamber. Ironically, the calmest wind exists inside the eye, but it's surrounded by the most violent. Inside the eye wall, wind speeds can exceed 100 miles per hour, even 150 miles per hour in major hurricanes. These winds are so tightly packed that they form a near-continuous wall of spinning air and rain, often just 10 to 20 miles wide. In satellite images, it looks like a perfect circle. On radar, it's a void, surrounded by crimson echoes of violence. And for those on the ground, the difference between eye wall and eye can be light and dark. 1 minute, winds strong enough to tear roofs and uproot trees. The next, eerie silence. The sun might even break through. This deceptive calm can last anywhere from 10 minutes to over an hour. But make no mistake, the second half is coming, and its winds blow from the opposite direction. This 180-degree wind shift is more than just dramatic, it's dangerous. Structures that survived the first half of the storm may have been weakened in very specific ways. When wind reverses direction, it applies pressure in new places, ripping apart what barely held together. Trees that bent with the wind before now snap against it. Storm surge may temporarily recede during the eye, only to rush back stronger when the opposite eye wall arrives. Meteorologists call this phenomenon eye wall replacement. It's common in strong hurricanes and involves the original eye wall collapsing and being replaced by a larger new one. Wind fields shift outward, storm size increases and intensity fluctuates. Wind behavior becomes less predictable in this stage, with sudden gusts and turbulence between the inner and outer eye walls. But it's not just near the core where wind patterns matter. Farther out, in the storm's feeder bands, winds also begin to rotate. These are not the steady spirals of the eye wall. They're broken, jagged arcs that extend hundreds of miles. Inside these bands, wind speeds can surge without warning. Waterspouts and tornadoes often form here, especially when the storm nears landfall and interacts with terrain. It's a chaotic ballet. On satellite, it looks elegant. In reality, it's turbulent. These spiral bands twist the atmosphere, dragging heat, rain, and momentum toward the storm's core. The winds within them curve dramatically, and embedded within some are mesovortices, tiny, violent whirlwinds that spin within the larger system. These micro-rotations can devastate localized areas, even far from the center. As the storm approaches land, wind signals change once more. Barometers drop faster. Surface winds accelerate and grow erratic. Trees bend not just from strength, but from shifting direction. The friction between land and air disrupts the lower-level flow, creating shear at the surface. In urban environments, buildings funnel wind into narrow streets, amplifying gusts. Meanwhile, over open terrain, wind can maintain its full force, pushing walls of water ahead of it. This is when wind becomes weaponized, not just through speed but through debris. Shingles become shrapnel. Tree branches turn into spears. Road signs, glass, and sheet metal slice through the air with deadly precision. In coastal cities, the first sounds of hurricane landfall are almost always wind. Windows rattling, doors slamming, transformers bursting under stress. But even as it wreaks havoc, wind reveals information. Emergency management teams rely on real-time wind data to track storm center shifts. Sudden drops in wind speed followed by calm, likely the eye. Wind gusts increasing faster than predicted. Possible eye wall replacement. Wind direction changing in quadrants, a sign of landfall and cooling. To trained eyes, these changes aren't chaos, they're coordinates. They help plot evacuation zones, estimate surge, and predict where structural failures are most likely. And once the storm passes, the damage left behind often mirrors wind's invisible path. Downed trees lean in one direction, power poles twist unnaturally, roofs are stripped in crescents, matching the curve of the eye wall's raft. Every hurricane leaves behind a wind signature. It's not just destruction, it's a map of pressure, motion, and force, etched into the landscape. And in the days that follow, as the winds finally fade, another shift begins. Stillness, no more gusts, no more sirens, just silence, and the reckoning of what the wind took away. But meteorologists, scientists, and survivors know, wind is not just an aftermath story. It's the first sign, the invisible builder and the constant narrator of the storm's life. And when the wind speaks, the planet listens. After the wind has spoken, through sudden calm, violent surges, and reversed directions, comes a deeper truth. Not all wind is created equal. Some signals whisper in advance, others roar without warning. But the most telling changes often go unnoticed by the untrained eye. They're subtle, hidden in layers, and they begin before the storm even earns a name. In the days before a cyclone forms, wind profiles reveal a quiet tension. Satellite buoys and weather balloons detect vertical wind shear. Differences in wind speed and direction at different altitudes. In a stable atmosphere, these winds line up neatly, allowing warm air to rise unimpeded. But when vertical wind shear is high, storms struggle to organize. It's like trying to stack a tower in a crosswind. It crumbles before it can grow. That's why early detection of decreasing shear is so critical. It's one of the earliest meteorological red flags. Scientists watch for upper-level winds slowing down and aligning with surface flow. These are the conditions that allow a tropical wave to rise straight up, uninhibited. They mark the transition from harmless clouds to a potential powerhouse. But there's another layer, less studied, more elusive: the Saharan air layer. Discovered through a combination of NASA satellite data and field studies like those led by Dunian et al. 2014, this dry, dusty air mass blows westward from Africa across the Atlantic every summer. On the surface, it seems like a desert's fingerprint on the ocean breeze. But it's more than that. The Saharan air layer, or sail, acts like a cap. It sits a mile above the ocean, dry and warm, suppressing convection. When sail is strong, it limits storm development by introducing dry air and enhanced wind shear into the mid-levels of the atmosphere. It's like throwing sand into a running engine. And yet, when the sail retreats or weakens, tropical systems often ignite. That shift is almost always accompanied by changes in mid-level wind behavior. The winds that once dragged dry air across the Atlantic ease up. They shift direction, and in their place, a smoother, more tropical wind profile emerges, one that carries heat and moisture instead of dust. It's subtle, measurable only by dropsondes and upper air weather models. But for meteorologists tracking pre-storm environments, it's a countdown. Meanwhile, closer to the ocean surface, local wind anomalies also emerge. In the hours before a storm organizes, you might notice that the breeze feels different. It's warmer, more humid, and curiously, often weaker. This softening of the wind, particularly in areas where trade winds usually dominate, can signal that pressure gradients are changing. The air feels heavier but moves slower, a paradox that often precedes explosive cyclogenesis. Fishermen in coastal villages have long noticed this shift. To them, it's not a technical anomaly, it's instinct. The air stops pushing back, the wind loses its rhythm, birds fly lower, The sky feels expectant. These ancestral observations align remarkably well with modern data, reinforcing that even today, wind still speaks to us if we know how to listen. As the system develops, upper-level cirrus outflow begins to spread outward like wings. This outward flow, driven by diverging winds near the top of the storm, is one of the final signs of a maturing hurricane. It indicates that the storm is successfully venting heat, dispersing the energy it draws in from the ocean. The wind vectors at this stage look like flower petals on satellite imagery, perfectly symmetrical, quietly terrifying. It's not all beauty, though. As the storm nears land, another wind-related threat begins to materialize: embedded tornadoes. Unlike the large spiraling winds of the hurricane itself, these are tiny, violent vortices that form in the outer rain bands, especially in the right front quadrant of the storm. Wind shear in this region is intense, and small pockets of instability can rotate fast enough to touch down. These tornadoes are brief, often lasting less than 10 minutes, but they can be deadly. They strike without warning, sometimes in places hundreds of miles from the storm's eye. They don't follow the usual logic of storm tracking. Instead, they erupt from chaotic wind interactions between land, moisture, and the hurricane's spinning arms. Mobile homes, power lines, and even reinforced buildings can be torn open. Again, wind reveals itself not just as a carrier of destruction, but as a creator. And yet, the most haunting winds come after landfall. As the storm weakens, starved of warm water and disrupted by terrain, the eye collapses. The symmetry breaks down. But instead of disappearing, the wind energy redistributes. It becomes erratic, directionless, gusty. This phase is sometimes more damaging than the peak, because weakened structures are now exposed to unsteady, pulsing wind bursts. Roofs that survived sustained winds now fall under gusts. Windows that held during the eye fail under the pressure of back-end turbulence. The storm doesn't end in a crescendo, it ends in static, in chaos, in wind that no longer spins but stumbles. In the days after, a new wind rises, dry, continental, cooler. It pushes the tropical moisture away. Skies clear. But in places where the storm passed, nothing feels quite right. Trees lean in the same direction. Billboards are twisted like aluminum foil. Fence lines are gone. The storm's path isn't just on radar anymore. It's written across the landscape. Insurance companies and FEMA investigators often study this wind map in reverse. By analyzing debris patterns, broken structures, and treefall angles, they can reconstruct the direction and speed of the storm's passage. Wind damage isn't random. It's highly structured, even if it looks chaotic. And each pattern tells a story of pressure, of angle, of duration. High-resolution wind modeling, combined with radar data, allows scientists to now build 3D reconstructions of wind behavior during hurricanes. These models help improve building codes, evacuation plans, and early warning systems. And they all start with the same principle. Wind is data, not just danger. It tells us what the ocean cannot. It speaks for the storm when the clouds are still forming. It predicts where power will fail, where water will rise, and where shelter will be lost. It is, in many ways, the voice of the planet in crisis. And sometimes that voice doesn't scream, it whispers, in a breeze that's too warm, in a shift that shouldn't happen, in silence that lingers too long. These are the early signatures of something massive, something in motion. Before the storm has a name, before the warnings go out, before satellites see the swirl, the wind knows, and the wind remembers. In the aftermath, when the winds have moved on, their echoes remain, not just in the wreckage, but in the data. Every gust, every shift in direction, every downdraft leaves behind a footprint. In meteorology, wind isn't simply movement, it's memory. And studying these memories helps decode how a storm grew, transformed, and ultimately collapsed. The most advanced forecasting centers, NOAA, ECMWF, the Japan Meteorological Agency, rely on high-resolution models that simulate wind behavior from the sea surface to the stratosphere. These models ingest real-time data from satellites, ocean buoys, weather balloons, and even commercial aircraft. And increasingly, they include data from drones that fly directly into storms. One such project, NASA's HS-3, Hurricane and Severe Storm Sentinel, deployed unmanned Global Hawk aircraft to fly above hurricanes for 30 hours at a time, collecting wind vectors, thermal profiles, and microphysics data. The goal? To understand what invisible wind structures cause a storm to intensify rapidly or fizzle out altogether. Because the truth is, many storms die young. Some gather heat, moisture, and pressure, but never organize. And often the deciding factor is wind. Too much shear and the updrafts tilt sideways. Too little outflow and the storm suffocates. Too much dry intrusion and the core collapses. It's a delicate balance, maintained second by second across miles of atmosphere. And when that balance tips, wind becomes the mechanism of collapse, or the engine of fury. During intensification, one of the most predictive signs is the formation of a closed, low-level circulation. It's a subtle process. Surface winds begin to spiral around a central point. At first, they're disorganized, scattered, gusty, uneven. But over time, the core tightens, the spirals become more uniform, and a signature shape appears on satellite imagery, the classic pinwheel. As this spiral develops, the Coriolis force kicks in more strongly. This invisible hand, caused by Earth's rotation, pulls winds into a curve. Without the Coriolis effect, air would simply rush from high pressure to low. But with it, the air spins. And the tighter it spins, the stronger the storm becomes. Wind, once random, now orbits with deadly precision. From here, the feedback loop begins. Warm ocean waters fuel rising air. Rising air lowers surface pressure. Lower pressure pulls in more wind. More wind accelerates evaporation. More evaporation fuels more clouds. And more clouds create a bigger engine. This is how wind builds a storm, not just as motion, but as mechanism. Once a hurricane achieves Category 3 or higher, wind stops being chaotic and becomes sculpted. It's shaped by the eye wall, the surrounding spiral bands, and the high-altitude outflow layers. Pilots in NOAA's hurricane hunters describe it as flying through architecture. Corridors of force, columns of turbulence, invisible structures made entirely of moving air. Inside the eye, winds are calm. The sky may even turn blue. But around it, the eye wall contains the most violent winds on Earth, rotating in near-perfect symmetry with gusts over 150 miles per hour. It's here that buildings shred, trees snap mid-trunk, and waves rise like liquid mountains. But the real horror lies just outside, the eye wall replacement cycle. As some storms mature, they undergo internal restructuring. The eye wall contracts and tightens, then weakens. A second, larger eye wall forms outside the original and slowly chokes it off. During this phase, wind speeds may momentarily decrease, but they return stronger than before. It's like a snake shedding its skin. Predicting these cycles is one of the great challenges in hurricane science. Models can detect wind field expansion, symmetry loss, and cooling cloud tops, but the exact moment when a new eye wall takes over, that's still the realm of uncertainty. And for coastal populations, it can mean the difference between manageable winds and catastrophic landfall. When the storm does reach land, wind meets resistance. Unlike over open water, where friction is minimal, wind over land slows down at the surface due to terrain, trees, and buildings. But this friction doesn't make the storm harmless. In fact, it can make it more complex. It creates low-level vortices, increases turbulent eddies, and sometimes generates rogue wind bursts, localized pockets of acceleration that hit like sledgehammers. This is particularly dangerous in urban environments. Skyscrapers and cityscapes channel wind into narrow pathways, accelerating flow between buildings over rooftops and through alleyways. These urban wind tunnels can create suction forces strong enough to remove roofing or break glass, even in lower category storms. The wind adapts to the landscape and often weaponizes it. As the storm pushes inland, wind continues its mission, carrying rain bands far from the core. In some cases, these outer bands can cause more damage than the eye wall itself. Why? Because they persist longer. They come in waves. They create flooding, landslides, and hours of constant pressure. And as wind interacts with terrain, hills, valleys, mountains, it creates secondary circulations. Downslope winds on the backside of a mountain range can accelerate dramatically, drying out as they descend. These are called foam winds, or lee-side jets. And in hurricane scenarios, they can produce fire risk, secondary storm cells, or sudden wind damage where no warning was issued. Wind is never uniform. It's shaped by everything it touches, which is why the end of a hurricane doesn't feel like a clean break. The storm may lose its name, its eye, its classification, but the wind continues. It moves north, it merges with cold fronts, it shifts into extratropical form, and in doing so, it carries storm energy into new regions. Sometimes it causes flooding in the Midwest, sometimes it spins off nor'easters, Sometimes it becomes the seed for a new system entirely. This persistence is why wind analysis doesn't stop when a storm does. Post-storm assessments involve forensic wind mapping, drone surveys, and radar echo replays. Engineers analyze wind load on infrastructure, utility companies study wind direction to improve future grid resilience, and meteorologists use the data to refine models for the next season. Every storm teaches a lesson, every gust leaves a clue, and together they form a story not of chaos, but of cause and effect, of physics, thermodynamics, and rotation, of a planet that breathes through movement. Wind is the breath of Earth. It builds, it breaks, and when it speaks, it tells us what's coming. We learn to listen. Even now, somewhere over the ocean, a breeze begins to shift. It's just a ripple, a sigh, a brush across the water, but it could be the beginning of everything. It's easy to fear the roar of wind once it arrives, to focus on the destruction, the chaos, the aftermath. But what makes wind so powerful isn't just speed or direction, it's transformation. Wind tells the story of a storm from start to finish, narrating its evolution from gentle disturbance to deadly force. It carries the memory of heat, the signal of change, and the voice of the earth itself. And those who listen, carefully, scientifically, urgently, can hear what's coming long before the clouds roll in. Throughout history, entire civilizations have depended on reading the wind. Sailors navigated oceans, farmers read signs in their fields, hunters learned to move with it, not against it. Today, we carry that instinct forward with satellites, Doppler radar, and high-resolution global forecasting models. But the principle remains. Wind is a messenger, and it doesn't lie. Even in a warming world where oceans rise and climate systems destabilize, the behavior of wind remains rooted in physics. It flows from high pressure to low. It reacts to heat, it curves with rotation. And as long as those laws remain, we can still find predictability in the midst of chaos. What we do with that knowledge, however, is up to us. In places like Florida, Louisiana, the Carolinas, and along the Gulf, wind has become a seasonal visitor, sometimes knocking gently, sometimes breaking down the door. Residents know the sound of shutters slamming, of power lines humming, of trees bending under invisible weight. These are not just meteorological events, they are cultural memories. And they shape how communities prepare, respond, and rebuild. But the rest of the country, those far from the coasts, cannot tune out. Hurricanes are not coastal problems. Their wind fields stretch hundreds of miles inland, spawning tornadoes, knocking out infrastructure, and flooding entire regions. In 2008, Hurricane Ike made landfall in Texas, but caused widespread wind damage as far as Ohio. In 2021, Hurricane Ida's remnants triggered tornadoes and flooding across the Northeast. The wind remembers no boundaries. That's why investment in wind science matters. It's not just about better forecasts, it's about better futures. Cities can design buildings that bend with the wind rather than break. Power grids can adjust to directional loads. Emergency response teams can pre-stage equipment based on probable wind paths. And individuals can make choices. Windows reinforced, trees trimmed, plans rehearsed. Preparation is never a guarantee, but it's always a difference maker. In a world where disasters are growing more frequent and more intense, preparation begins with understanding. And understanding begins with attention. To the subtle, the small, the early. A breeze shifts direction, a gust feels warmer than usual. The trees don't sway like they used to. These signs, once dismissed, now demand interpretation, because wind isn't waiting. The science is clear. As global temperatures rise, the atmosphere holds more moisture and storms gain more energy. Wind fields are expanding, shear patterns are changing, the jet stream is behaving differently, and the traditional rules about when, where, and how hurricanes form are evolving. But the tools are evolving too. Machine learning is helping forecasters analyze wind trends faster and more accurately. Real-time satellite data is filling in gaps over remote oceans. Crowdsourced data from smartphones and home weather stations is improving micro-scale wind modeling. The field of atmospheric science is not just observing the wind, it's learning to anticipate its movements. Even artificial intelligence now plays a role in predicting wind shifts before they show up on radar. At NOAA, new AI-driven models have started integrating wind anomalies and thermal deviations from ocean sensors to estimate the probability of rapid intensification. It's not perfect, but it's faster, And in the race against a strengthening storm, faster can mean lives saved. Still, even the most advanced models have limits. Wind is influenced by terrain, moisture, atmospheric layering, solar heating, and distant jet streams, variables that can shift by the hour. No model can predict every gust, but collectively they form a cone of probability. And inside that cone is where human judgment, preparation, and resilience must live. Which brings us to the final truth. Wind will always be with us. It shaped our past, pushing explorers across oceans, scattering seas, carving canyons. It powers our present through turbines, weather systems, and clean energy. And it warns us of our future, stormier, less stable, but not unmanageable. To manage it, we must first respect it. Not just in the moment of disaster, but in the quiet hours before, when the ocean is still, when the breeze is soft, when the only sign is a shift in the air. That's when decisions matter most. Will we study the patterns or ignore them? Invest in science or cut corners? Train communities or gamble on luck? The answers won't stop the wind, but they might make it survivable. And maybe over time, they'll transform how we live with it, not as victims, but as witnesses. Not just reacting, but adapting. Listening to the language of the earth and answering with wisdom, not fear. So the next time you step outside and feel the wind change direction, pause. Notice, because that moment, fleeting, invisible, might be the very beginning of something, or the warning before it begins.